Hello everyone, am I audible? Hello. So I am Mr. Shroff and today we'll be studying trees. Okay, so without a further ado, let's start. Okay. So today we'll be studying trees, okay? Okay, so now let's move to lowest common ancestor. So first, can anybody tell me what is an ancestor? Hello? Okay, so any parent that is called an ancestor, right? So if I take root and node, then all the nodes that lie from root till the parent are termed as the ancestor. Is this clear to everybody? Hello? Just a second. Am I audible to you guys? Okay, okay. So now let's talk about lowest common ancestor. So for two nodes n1 and n2, the lowest common ancestor is that node which is ancestor of both n1 and n2, and it is located farthest from the root. It is located at the farthest distance from the node. So for example, let's say we have nodes 4 and 5. So the LCA would be 2 because 2 is ancestor, it is parent of both 4 and 5, and it is located farthest from the node. If you see 1 is also an ancestor of both of them, but it is not lowest, right? Same way, if we see 5 and 6, the lowest common ancestor is 1. Is this clear to everybody? What exactly is the lowest common ancestor? Hello? Okay. So now we'll be studying how to find the lowest common ancestor, right? In the next slide. So first we'll study what is the brute force method, and then we'll be studying what is the optimization of that. Okay. So this, as I have said, LCA of two nodes n1 and n2 is the lowest point of intersection of path from root to n1 and root to n2. Is this clear to everybody? Right? If I have path from root to a node n1 and a path from root to n2, then the farthest point of intersection is the LCA. Is this clear to everybody? Right? And this property should also be very obvious, right? If A is parent of B, then LCA of both of them is B, right? A parent of A is B, then LCA must be B. Is this clear? The second point. This is very obvious, right? Because B itself is the ancestor of A, right? Hello? Okay. So this means it is clear to everybody that what exactly is LCA. So now can anybody suggest a method to find LCA? Like the basic one, using the concept you have studied, like DFS, BFS. You all have studied, right? DFS. Hello? Have you all studied DFS? Hello guys, am I audible? Can anybody suggest a method to find the LCA using the concepts you have studied? Okay, so I'll tell something. So suppose you want to find the LCA of, let's say, node 4 and 5, right? So what you do is you find the path from root till 4. Can you do this using DFS? Hello? Can you find the path from root to a node using DFS? Yes or no? Hello? Am I audible? Hello guys, am I audible? So what I'm telling is, okay, do you know how to find the path of between root and a node? Like let's say you want to find this part 1, 2, 4. How would you do it using DFS? Do you guys know this? I did not get it. Can you repeat it again? Okay. ठीक है. सही है मतलब एलसीएस ढूंढने का तरीका ना एग्जैक्टली. सो डिड everybody got that? Hello. So basically, what he said was that we'll find the path, like we'll take two of these nodes and we'll start taking their parents, right? And the moment, like what he said was, we will first find the path from root to both of the nodes, and then we'll start comparing the paths starting from the root node. And the moment where the two nodes differ in the path, the node just above that would be the answer. So, for example, the path from 1 to 4 is 1 to 4, right? 1 to 4 is the path, and here 1 to 5. So, you start comparing both the paths. One node is common in both of them, 2 is common in both of them. Then comes 4 and 5. So, here is where the two paths differ. So, the node just above that, that is 2, is the answer. Is this clear to everybody? Hello? Okay. So this is a brute force way of finding the lowest common ancestor, right? This will do the job in O of n time. Now we need to optimize it. So we'll study how to do that. Okay. So the technique to do that. So you can find the kth parent of any node in log k time using binary lifting. So here we'll be using binary numbers. So as the name suggests, it is binary lifting. Okay, so let me tell you first what is this thing over here. Ancestor node 0. What does this mean? Ancestor ij. So ancestor I j. What does this mean? So ancestor ij means what is the ancestor of node I, what is the 2 raised to power jth ancestor of node I. So if I say ancestor 1 0 means the first ancestor of node 1. When I say ancestor 2 3, that means the 8th ancestor of 2. Is this clear to everyone? What does this mean? Okay, so first what we do is we find the 0th ancestor. We know that is the parent itself, right? Everybody knows how to find parent using DFS, right? Hello. So first we find the parent of each node and we'll store ancestor of node 0 to be the parent. Okay, now I'll tell you one thing. Suppose if I know the ancestor of suppose I know the jth ancestor of every node, right? So can I find out the j plus 1th ancestor? Like if I know ancestor ij for j is equal to 2, then can I find out the ancestor i3 using the data we have? Okay, so let me give an example. So suppose let's say I have a tree like this and I know all the second ancestor, like ancestor of where j is equal to 1. I know all the 2 raised to 1th ancestor of all the nodes. So using this data, can anybody tell me how would we find the 2 raised to 2th ancestor? Right, suppose for this node I know that the second ancestor is this one. For this node I know what is the second ancestor, this one. So can I find out how would we find the 4th ancestor? Exactly, right, great. So if we know the second ancestor of every node, then the second first we'll find the second ancestor of the node, and then we will find the second ancestor of that ancestor itself. So this is the second ancestor, and its second ancestor would be the 4th ancestor. Is this clear to everybody? Hello. Okay, is this clear to everybody or not? Hello. So okay, so for x from, so first what we do is we know that any ancestor of root is the root itself, right? So there is no need to do anything for root. So we do this, we initialize every ancestor of root to be equal to root itself, and then what we do is for every x from 1 to log n, we know that j will range from 1 to log n, right? We say that the ancestor of the x ancestor of the node is the ancestor of node x minus 1 and x minus 1. Did you know how it came? I just now discussed it. We first find the x minus 1 ancestor and we again take its ancestor, right? Ancestor of ancestors. Is this clear to everybody? Okay. So after doing all this stuff, we know what is the x ancestor of node, where x is a power of 2. 2 raised to 1, 2 raised to 2, every ancestor we know, right? Okay, now if we want to find the kth ancestor, how would we do that? It's very simple, right? We'll express k in binary form and then keep on finding its ancestor, right? So if the ith bit of k is set, then we will move to ancestor node I. Is this clear to everybody? Let's say you want to find the fifth ancestor. So 5 is equal to what? 101. Okay, so first we'll find the fourth ancestor because here it is 1, and then we'll find this ancestor, first ancestor. So together we can get fifth ancestor or not? Okay, so this is what we do. So the process to find kth ancestor of any node is this one. Is this process clear to everybody? Okay, so let's move ahead. So now we'll be using this data to find the lowest common ancestor, right? This is the pre-processing that has to be done. Okay, now let's move ahead. So now we'll be finding the LCA, the lowest common ancestor, using binary lifting. Okay, so let's say you have two nodes U and V, and let's say you run one DFS and find out the level, the depth of the node. Okay, you can do that using DFS, right? Okay, so I'll explain this procedure using an example. Okay, so let's say I want to find the LC of this node and this node. Okay, so we know what the brute force method is, right? We will first move this node till this level, right? So it will be here over there, right? And then we will keep on moving each nodes until we find the common node. We know this process, right? Hello. So first we will move up until we get at the same level, until both the nodes are at the same level, that is till here, and then we'll keep on moving upwards. We'll keep on moving each node upwards until we find that both the nodes have become equal. So here the LCA would be this node over here, right? Okay. So first case, we'll find. So we know that first we need to equalize the levels of both the nodes. So how will we do that? We'll find a difference in levels, right? So if we know, we say u and v, so if we say if level of u is greater than level of v, we'll swap both of them. So we'll assume that the u is always at higher level than v. If they come out to be opposite, then we'll just swap them, and then we'll move this v node to the level of u using this funda, right? If level v minus power is greater than level u, then we'll move to the kth ancestor. This will keep on doing until both level v and level 2 become equal. Is this clear to everybody? Right? Till both of them become equal. Okay, now there can be two cases. Either suppose that this node is the ancestor of the other node, then when we do this process, we'll get the LCA itself, right? So if u and v both become equal, that means u is the LCA, right? And if that is not the case, so let's say we move till this level. Okay, we move to this level. So now both the levels are equal. If u and v become equal, then we know that that is the LCM. If they are not equal, then what we'll do is we'll start from the last bit and move till 0, and we'll see if on moving that many steps are we getting the same ancestor or not. If we are not getting the same ancestor, we'll move it upwards. So for example, let's say we start from 8. So we see that, let's we start from 4th. We know that both the 4th ancestor are equal. So we will not do anything. Then let's move on to the second ancestor in this example. We see that this node second ancestor is this one, and this node second ancestor is this one, right? So they both are not equal. So we will replace u with its ancestor and v with its ancestor. So now the new u and v are, this one is u and this one is v, right? Again we'll repeat the step, and now we'll see for k is equal to 1. We see that both the ancestor are equal. The first ancestor of u and the first ancestor of v are equal. So again we won't do anything, and we'll continue that. So finally we'll get this to be u and this to be v. So if you observe one thing, we'll always get u and v to be the node just below the LCM, right? We will always repeat this process when both the ancestors are not equal, right? So the final values of u and v would be one below the lowest common ancestor. So if we simply give the parent of u, then that would be our answer. Is this process clear? Okay, I'll give an example. I'll give one more example and tell you what exactly I have done. Okay, so let's assume that we need to find the ancestor of the LC of ninth node and 7th node. Okay, so let's do it step by step. So we know that level of u is greater than level of v, so we'll step u of v. So now this would be u and this would be v. U is always at higher level as compared, u is always at lower level as compared to v, right? Now we'll first try to equalize both of their levels. So we see that what is the difference between the levels? 1 2 3 4, so it's 4. Okay, so we'll start from log n. Like what is log n is 8, so it's 3, so 2 to 0, and we'll try to equalize that. So we see that level of v, what is the level of 1 2 3 4 5 6, level of v is 6. 6 minus 4, it is equal to 2. Yes. What is this level? 1 2 3 4 5 6. What is this? 1 2 3 4, right? So we see that this minus this, it is greater than, so we'll move this 9 to 4. This process is clear to everybody or not? No, sorry. So first we start from 4. We see that 6 minus 4, that is less than, so we won't do anything. We then move to 6 minus 2, that is 4th level. This level is exactly equal to the level of 7, so we will move 2 steps upwards till here, 6th node. So now both of their levels are equal. Is this clear to everybody? First step. 9th node was here, 7th node was here. We first need to equalize their levels. So what we did was we started from the highest power of 2 till 0 and kept on decrementing the, kept on moving 9 until both of the levels are equal. So now our u is this one, 7, and our v comes out to be 6 now. Okay, so we see that u and v are not equal, right? So we'll move on to this part. Okay, now let's start again. We repeat the process. We see the fourth level. The fourth level of 7 and fourth level of 6 are both equal to 1. We see that. Okay, so we won't do anything. Now we'll see the second level. We see the second level of this 6 and second level of 7, both are again equal, both are being equal to 2, this thing. So again we won't do anything. Now we check the first level. We see that the first level of 6 is 4, first parent, and the first parent of 7th node is 5. So we see both are not equal, right? So we will move this to this and this to this. So now our u and v are, u is 5 and v is 4, right? Okay, so now we can't do anything. So we finally have u is equal to 4 and v is equal to 5, and the parent of u would be 2, which is our answer. Now is this process clear to everybody, what we did and how we did? Anybody having any questions to ask? Hello? Okay. So everybody got know how to do. Okay, let's move ahead. Okay. So you try this first question, everybody. Can anybody tell me the approach? How would we do that using binary lifting? The concept that we just now studied. Can anybody solve this question? First one. I'll give you 5 minutes to think. Please try this question, everybody. Hello. Am I audible, visible? Okay. So please try this question. Anybody having any approach in mind? What to do? Yeah. Yeah. So what you are telling actually is basically an O of an approach, right? I want you solve using binary lifting. We saw that how we converted log O of n to O of log n, right? Using that new array that we created. Can you use that similar approach to find this? That is what I want. You got that or not? What you are telling is basically that O of n approach, right? Every time we need O of n time to do that. Okay, so think O of log n approach using binary lifting. We just now studied, right? Mm-hmm. Yes, yes, you're close to that. So what you are telling is basically we'll create another array, right? Similar to what we create. Okay, that is exactly the approach, right? Right. You are on the right track. Okay. Okay, so let me explain the approach to everybody. Okay. Hmm. So, as we said, so in order to do that, we'll create one more array. We'll create one more array named Zor. Zor I J. What will this store? This will store Zor of all elements. Zor of 2 to the power j elements above ith node. Getting the point? So if I have a tree like this, hmm, let's say I have, okay. So if I have a tree like this, what will Zor of 4 1 store? Zor of 4 1 will store 4 only. What will Zor of 4 2 store? Zor of 4 2 will store the Zor of 4 and 2, like something like this. So let's say I have a tree. I'll give an example and tell you. So let's say I have this node. Let's name this node as 1. So what will Zor of 1 0 store? It will store Zor of all values starting from this node till the 0th ancestor. So which is 1 itself. Right? We will not include that ancestor. We'll simply include all the nodes below the ancestor till that required node. What will Zor of 1 1 store? So Zor 1 1 will store the value of 1 and Zor of these two nodes. Getting the point or not? Zor of 1 3, sorry, Zor of 1 2, what will this store? It will store the Zor of all these three nodes excluding the ancestor. Getting or not? Okay, so that is basically what we are going to do. Okay, so can we write something like this? Zor of node 0 is equal to node. Is this true or not? Zor of node 0 is equal to node. Right? Right or wrong? Okay. Here also we'll write Zor of root. But this doesn't matter. No need to worry about this. Okay. Now what we'll do? So if we remember the process, what we did was ancestor of node x is ancestor of the x minus 1. We did that. So can I write something like this? Zor of node x is equal to Zor of node x minus 1 Zor Does everybody get this? How I came with this? Hello, right? So the same concept. First we find the Zoro of 2 raised to x minus 1 element starting from the node. Then we'll take its 2 raised to x minus 1 ancestor and again find the Zoro of 2 raised to x minus 1 above it. So in total we found out the Zoro of 2 raised to x minus 1 plus 2 raised to x minus 1, which is equal to 2 raised to x minus 2 nodes, 2 raised to x nodes, right? Yes or no? Is everybody clear with this? What I this over here? Hello. Okay. So if you have this tree, mm, I'll draw one for you. Okay. Let's say I have this tree. Okay. So, let's say I want to find the XOR of this node. Node name is V. XOR of V 2. So it will basically contain XOR of all these four elements, right? So what will XOR of V2 contain? These two. XOR of these two elements, right? And we'll move on to the ancestor. What will the XOR of ancestor of 2 will store these two elements, right? So XOR of both of them will store the XOR of all the required elements or not? We break it into two parts, 2 raised to j minus 1, 2 raised to j minus 1, and add them up, we get to XOR of all the 2 raised to j nodes. Getting? Okay, fine then. Okay, so now we have XOR of all 2 raised to x elements present with us. Now we'll simply repeat this process, what we did for LCA. Now, everybody tell me, if I want to find the XOR, where is the question? So if I want to find the XOR of path from U to V, so can I say something like this, that in order to find XOR from U to V, first we find the XOR of all elements from U to LCA, and then we find all the XOR of all elements from V to LCA. If we XOR both them up, both of them, then we'll get our required answer. Is this true or not? XOR of U to V is equal to XOR from U to LCA. So XOR of V to LCA. So we'll get XOR of all elements from on the path from U to V. Yes or no? So that is what we are going to do. Now we'll move to this LCA code. I'll copy this one. Okay. So what we'll do is we'll keep on moving. We'll initialize a value over here. Answer. Okay. And we simply keep on XORing the elements till we get the LCA. Answer is equal to answer XOR, right? And here also I'll add like this. Answer XOR. And then XOR. So everybody got what I did over here, right? Now we'll start the process of finding the LCA. So what we did initially was like the node, first we are trying to equalize the level of both the nodes, right? So we would have to shift the nodes. So during that shifting process, I kept on adding the XOR of all the elements, right? Now once we move to the equal element, then what I'll do, then again find the XOR. So after we do this process, we have XOR of all the elements excluding the LCA. We don't have the XOR of LCA, right? Then I'll find the XOR of LCA and then return it. So I'll tell you what I did. Uh, okay, so let's say I want to find the XOR of all elements from on this path between these two nodes, right? So first, what we need to do to find LCA, we need to bring this node to the level of the other one, right? So in that process, first we will move two steps up to this one, and then we will move one step up, right? So when we move these two steps up, we will store the XOR of these two elements in our answer, right? Using the code that we did. Getting or not? So then again we move one step upward, we will store the XOR of these two elements. This one element only this element, right? Then we move to this node at equal level, and then we again move upwards. We see that the second ancestor of both the nodes is equal, so we won't do anything. We then move to the first ancestor, right? So we'll again store the XOR of these two elements, these two and these two, right? And we have finally reached this level here and here. If you observe carefully, we haven't taken this node into account, which is actually the LCA. So that is why I did finally answer is equal to answer XOR parent u, because parent u is basically the LCA, right? And we need to take it XOR. Getting or not? And then when we complete this process, we have the we have the XOR of all the elements in the path. Yes? Getting the point or not? Okay. So okay. Can you think of the second question using the similar concept? What chain will we make in that? Hello? Exactly. So if so, what we can say is max of max node max node I is equal to max node I minus one comma max of ancestor node I minus one. Yes or no? Okay. So everybody got this concept or not? How we did using binary lifting? For any property that we want to find, we make up on one more array storing the answer to that properties, and then we use the concept of binary lifting to do that. If it is for XOR, we'll make a new array XOR. If it is for max, we'll make a new array max. If it is for sum, we'll make a new array sum. Right or wrong? Okay. So now we have Euler's tool. So Euler's tool, as you can see, suppose the image itself is very clear what exactly is Euler's tool. So Euler's tool is basically a flattened version of the tree traversal, right? It is the flattened version. So if you can see, first we start from node 0, then we move to 1, then we move to 3, then we come back to 1, then we move to 4. So you can see everything is getting stored over here. If you look at this visual image, is everybody seeing the image? Okay. So why we use Euler's tool? See, if we want to find something related to some subtree, let's say we are given a subtree and we have to find the max of all elements in the subtree. and we can update the elements as well. So in that case, we can convert this tree into a flattened form and use the concept related to arrays to find them. Say for example, you want to find the subtree, so we'll identify the subtree in the flattened version of the tree, and then we can apply segment tree or anything like that to find the queries. So for time being, you just understand what exactly is a Euler tool. You won't be able to do these questions because they require the concept of segment trees. The moment the segment trees would be taught, we'll be doing these questions, right? So for time being, we will skip that because this requires segment trees. But you guys tell me, is Euler's tool clear to everybody or not? What exactly is a Euler's tool? Right? So using Euler's tools and something like segment trees or sparse trees, we can do these two questions, mean in a subtree and sum of nodes and all that stuff, right? With updates, right? If in this question it is given find sum of nodes from root to u without updates, then we can simply use a DFS to do that, right? But here it is given with updates. That's why we require segment trees and this Euler's version. Getting the point? Okay, guys. Thank you, everybody. We are done with the class. See you next week.